we can find the area of a region between two polar curves by extending the definite integral of finding the area of a region enclosed by one polar curve, which we derived as follows. So recall that we summed up the area of a bunch of triangular slices from some angle theta A to theta B. So let's just call this red curve, curve A. And if we apply the same definite integral to a second green curve, so the area enclosed by that curve can also be written using the same definite integral. So therefore, if we subtract the area within the red curve from the area within the green curve, then we obtain the area of this region between those curves. So therefore, our definite integral to find the area between two polar curves between angle theta A and theta B is written as follows. So typically you'd find these angles where the curves intersect, and you'll be able to evaluate the integral. Let's calculate the area of the region inside the limacon and outside the circle. So that would be this region over here. And recall that the area between curves is defined as follows. So if you substitute r equals 3 into this equation, then you can see that the curve intersects when cosine theta is 0. So therefore theta is a multiple of pi on 2. So these are the intersection points over here. So what we do is integrate from minus pi on 2 to pi on 2. And we're integrating radius of curve A squared minus the radius of curve B squared with respect to theta. And now you can expand and simplify this, apply your trig identities, and you'll be able to obtain the area. Let's calculate the area of the region bounded by the inner and outer loops of the limacon. So because we're looking at one polar curve, we're going to use the area integral for a single polar curve. So if we first integrate from theta equals 0 to theta equals 2 pi on 3, and we integrate r squared with respect to theta, well, that's going to give us the area of this top half of the curve. And now if we subtract the area of this region by continuing to integrate from 2 pi on 3 to pi, and we integrate r squared with respect to theta, well, that's the same thing as subtracting the area of this region due to symmetry. So what we've effectively done is obtain the area of this top half of the curve between the outer and inner loops of the limacon. And if we multiply this result by 2, well, that's going to give us the area of the entire limacon between the outer and inner loops. So if this is not clear, post your questions in the comments. Let's calculate the area of the region inside the lemniscate and outside the circle between theta equals 0 and theta equals pi on 2. So what we're looking at is the first quadrant and this part of the curve. So we need the intersection point between the two curves, and we can do that by substituting r equals root 2 in this equation. So what we get is root 2 squared is 4 cosine 2 theta. So cosine 2 theta is equal to 1/2. And for this to be true in the first quadrant, then 2 theta is equal to pi on 3. and therefore theta is equal to pi on 6. So as we can see, the curves intersect when theta is 30 degrees. And now we can apply the area integral to obtain the area between those two polar curves. So we're integrating from theta equals 0 to pi on 6, and the radius of the outer curve squared is the lemniscate, so that's already squared, so we don't need to square it again. And then minus root 2 squared integrated with respect to theta. And that's going to give us the area of that region.